and welcome back to another video. This is me, Clara Barker, and this is my series of science videos. So in these videos I've been talking for the last few weeks about thin film deposition. That's the core of what I do in my day-to-day job, and it is what I've been doing for the last sort of 15 or so years. So thin film deposition is a very, very important part of my scientific career. However, I am the manager for the Centre for Applied Superconductivity in the Materials Department of Oxford University. So we make thin films, but why do we make them? What are the films that we make? What are the applications, and how do those materials work? And as you can probably guess by my working in the Centre for Applied Superconductivity, we make superconductors. So we make bulk superconductors, but we also make thin film superconductors as well. And we actually use the techniques pulse laser deposition and magnetron sputtering that I talked about in previous videos. And I might actually put a video out later on explaining a little bit more about how we make superconducting thin films in particular, because it is quite interesting in itself. So I thought let's take a few weeks to talk about superconductivity, and it's not just going to be one video because there's actually a number of aspects when it comes to superconductivity that I want to talk about, and I'm going to break that up into different videos. So without further ado, I think that we should probably get on with it, right? Okay, so superconductors. So these videos are going to be talking about superconductivity, and I think anyone that knows anything about superconductors, even if you know the very basic thing, you probably have. It's because you've probably seen some sort of experiment like the one in the video. So what we have here is a magnetic track. So it's a track made of magnets, and above it we've got a superconductor that's been cooled down, and that has trapped a magnetic field, and it levitates and floats above the track, hopefully, whilst it is cold. Now, I'm going to be talking about exactly what's going on with that and these magnetic properties in the next video, because in this video, whilst that is the thing that we probably know visually, I'd actually say that more important is the electrical properties of superconductors. And so that's what I'm going to talk about today. And I'm going to take us back a little bit and start at the beginning. What is electrical conductivity to a certain level? So on the screen, I've actually got a series of balls. Now, if we imagine that we have a wire, a copper wire, as most conducting wires are made of, this is made up of a whole bunch of atoms, copper atoms, and they're arranged in a particular structure. Now, I've said that with material science we can change the structure. However, in this case, we're just going to be talking about a structure rather than going into specifically different structures. So we've got this structure that's made up of all these copper atoms. But each of these atoms isn't just one thing. It's actually made up of things itself. So the level that we're going to be talking about is that we have the nucleus in the center. So this is the protons and the neutrons of the atom, and for different materials we have different numbers of protons and neutrons, and then we have the orbits of electrons around the nucleus. So the electrons actually circle around the nucleus. And these electrons, again, we have different numbers depending on the material. And they arrange themselves in layers. So they arrange themselves in rings. So you can only have so many in each ring, and then you grow another ring, as it were. So we have 2 in the outer ring. And then if you've got more than 2, then you have another ring of 8. And then if you have more than 8, then you have another ring, like the example I've given here. And conductors, what you find with conductors is that they've got 1 or 2 electrons in the outer ring. Because there's only 1 or 2 in the outer ring, what we find that it's actually quite easy, relatively, to pull the electron off. So that's what we do when we're using to conduct electricity. What we do is we apply a voltage at one end, and there's a potential difference between the voltage and the other end, which might be at ground or some other level. It's at a different voltage, and there's a current that travels through the material, which is this transport of electrons. And because it's not just one atom that is losing an electron, but all the atoms are losing an electron, we have what we used to refer to in school as a sea of electrons. So this is our charge. This is where our current is coming from. And so that's what's going on at a very sort of basic level. But if anyone knows anything about conducting electricity, we know that we have this thing called resistance. Basically, not all of the electrical energy that's put in comes out the other end. We lose some of this energy along the way. We don't lose the energy, it's just converted from electrical energy to other forms. So if we have a lamp or a bulb, we convert some of this electrical energy to heat and light, for example. And what's actually going on? Well, our atoms, I said that we've got this atom and they're in this sort of structure. But what we didn't say is that the atoms are all bouncing around, they're all vibrating. Now, they're not, synchronized as they are in my example, but it's easier to animate it that way. But actually, each of these atoms is vibrating individually. It's all bouncing around in its own little way. And so when the electrons are traveling through, what we actually see is there's a whole bunch of collisions. The electrons are hitting these vibrating atoms and they're getting knocked off and traveling in different directions. And as we're doing this, basically this is resistance. We're losing this electrical energy and we're converting it to heat or light. So we have some electrons that are being converted, and that's our resistance. And then we have some electrons that are traveling from A to B, and that's our conductance. It's the opposite of resistance. So we've got a conductivity and a resistivity. So this is great. So that's what we're starting with. That's the basic principles. Now, what we see is that at different temperatures, the vibration of these atoms changes. So as we cool it down, the actual vibration slows down, so that once we're at a very low level, the vibration is a lot less. They're not bouncing around, they're not moving around quite as energetically because we've removed a lot of the energy. This is one thing that happens, but with superconductors, there's this extra little thing that happens, that once we reach a particular temperature, once we go down and get to a cool temperature, then all of a sudden we start to find that we have additional things going on. So let's look at our electrons again. So in this case, we've got a superconductor and we've cooled it down. I've given you an example here of minus 210 degrees C or 63 Kelvin, and I'll explain why I've sort of used that as an example in a minute. So we've got these things are vibrating slowly, but we've still got these electrons. But rather than going through individually, what they do is they go and they get themselves a friend. Each of these electrons goes and says, hey, you, be my buddy. It's a buddy scheme for electrons. This is strange. This is unusual because two electrons both have a negative charge. So you wouldn't expect them to form a couple, form a pair, but they do. And that's very peculiar for superconductors. And we actually call these Cooper pairs. And I must say that these can be a few nanometers apart, which is actually quite massive, but we know that they're still a team and they're traveling through together. And what's even more unusual is that because they have formed up and formed this pair, now it takes an awful lot more energy for us to knock them off course. Whereas previously with the one electron, it would only take so much energy to divert the path. Now with them in these pairs need an awful lot more energy to divert their path. So now they're traveling right the way through. And you'll see that they're no longer getting bounced off course. We no longer have resistance. And in fact, in superconductors, we have zero electrical resistance. They are really good conductors. They are superconductors. So by forming these pairs, these Cooper pairs, they're able to travel through. And so the what we put in at one end is what we get out at the other. And what's really interesting is that we can close off our superconductors. So I said that to have this current flowing, you need to apply a voltage to one end. But actually, with superconductors, yes, you still need to do this, but then you can close the circuit, remove the voltage, and you'll have a perpetual current. This current will carry on traveling through a closed loop circuit, even though we no longer have that voltage. Now, obviously, for the sake of energy transport, we want to put the energy in and getting it out somewhere. But some of you may also realize that if we have a current traveling in a particular direction, then we can also generate a magnetic field, and that's going to come into play later on. And it actually allows us to generate very high magnetic fields. But this isn't the same magnetic properties that mean that our magnets float. So you're not going to get that in the next video. It's going to be in the video after that. See, you'll have to come back. So this is great. So by forming these pairs, we've lost our resistance. So the electrons are traveling through the system really nicely. And there's also an extra little quirk, shall we say, that these electrons are they have a negative charge. And I've been talking about them as atoms, but what we have to remember is that they have lost an electron. So now these are actually slightly positively charged ions. And so as our electrons move towards these ions, what we see is that there's local attraction. So the ions are actually drawn and pulled and attracted towards the electron that's traveling through. And that means that we've created a slightly positive area so that the second electron in the Cooper pair is attracted to that slightly positive charge. So the first one attracts the ions, and then the ions being slightly closer together attracts a second electron. So it feeds into itself. So it sort of almost squeezes the electron through, as it were. Although squeezing is the wrong term. But it's an interesting concept that, electrons travel through, draw the ions in, the ions then draw in the second electron. So, like I say, superconductors, they've got these really amazing properties. And what's interesting about this is that we have zero electrical resistance, which means that if we need to supply a particular current to something, we can get the same current with a superconductor that is much thinner than a normal conductor. So I've got a picture on the screen, and this is provided by my colleague, Professor Susie Speller. And in the example, we've got this big bulk of copper cables, and then we've got this thin superconducting cable next to it. And there's a huge difference in the cross-sectional area of these two wires, but they're actually capable of conducting the same current. So this is great. If we were able to swap our conducting cables, our energy production cables for superconductors, then we'd have a lot less copper being used. We'd have much smaller cables. In fact, we could bury them rather than transporting them in overhead pylons. Of course, we've got to cool down the superconductors as well, and so it isn't necessarily just a case of we can replace all our cables, but it's an interesting concept. So as we go along and we talk about applications in another video, we're going to see how we can apply this. So this is really exciting. Now, it doesn't mean that there isn't despite the fact that the cables have zero electrical resistance, it doesn't mean that they can carry infinite current. There is actually a current limit, and at a certain point, the current limit overcomes the superconducting properties of the material, and then we introduce resistance. And that's quite a complicated thing, but just know that we can carry high currents in these superconducting cables, but we do have limits, and that actually depends on magnetic field. It can depend on the current. It can depend on the pressure, even, and certainly it depends on the temperature. So that's really cool, I think. So let's go back to a single screen. Right, so that is sort of a real basic overview of what's going on with conductivity in superconductors. Now, I actually realised I didn't talk about why I used an example that was around 70 Kelvin. So for those that don't know, which I'm assuming is most of you if you're watching this video, if you have superconductors, quite often traditional superconductors, you've got to cool them down to around, I don't know, 7 Kelvin. So we're talking, you're talking minus 270 degrees Celsius, which is, well, it's very cold, obviously. It's moving towards absolute zero. In our group, we mainly concentrate on high temperature superconductors. And what makes a superconductor high temperature superconductors is that instead of having to be cooled to around 7 Kelvin to switch on the superconducting properties, we actually switch on at around 70 Kelvin. So only minus 205 degrees Celsius. Now you might say that's still cold, and it is, and you might say that's not high temperature. However, it's much higher than the other superconductors, but what's even more important is that that's the temperature we can get to by using liquid nitrogen. Nitrogen's all around us. It's much easier to cool things down with liquid nitrogen than things that have to be cooled down to lower temperatures. So actually, it's a really specific reason why all of a sudden 70 Kelvin becomes high temperature, because we can use liquid nitrogen. And that's fantastic. That's really, really useful. Yeah, so that's quite a lot. So like I say, in the next video, I'm going to be talking about the quirky magnetic properties. And then after that, I'm going to be talking in another video talking about the generated magnetic field. So with that, thanks for watching. Hopefully you'll tune in for sort of part 2 on superconductors. And with that, take care and see you again soon. Bye bye.